we, as Glenn mentioned, we had an ARM project. This is the Advanced Robotics and Manufacturing Institute out of Pittsburgh. We've had this is a follow-on to a project we had kind of the year leading up to when Hammer started, and then we got this follow-on. Glenn said Brian Thurston was on the team. My colleague Adam Bynack here in the Ames lab was on the team, and so we've demonstrated now an incremental robotic forging system with integrated heating that can actually heat up steel. And so I'll show you a little video here. This is an hour-long forging session that we've sped up to 20x. So you're going to see a 3-minute video of some steel getting real hot and getting smashed around. And so I'll ramble while the video is going. So I'll just go ahead and start it up here. You're going to see the robot come in, and it's sort of putting this part inside of the induction coil. You can see it already getting hot. Again, this is 20x, but it's about 5 minutes is the initial heat. So that when this thing pulls out, that was 5 minutes. After that, the heats aren't nearly as long. You've got a couple views over here where you're seeing perpendicular to the press, and then kind of down the end of the press, or sort of looking down the rod geometry here. And so you can start to see, we're getting it real hot, and you can really see the volume change. We take a 7-inch long, 2.5-inch diameter billet, and we lengthen it to a little over 12 inches. So we get almost a 2x elongation. You can really see that material starting to stretch there. We cog the geometry down from that 2.5 inches to something as a little bit smaller than 1.5 inches in the sort of narrowest region. So getting a significant amount of deformation. This is a sort of little totem pole geometry. It's to mimic an Air Force part that Glenn's talked about numerous times, the sort of tie rod geometry that they've been interested in. The tie rod's kind of boring. It's just a cylindrical round rod. So we wanted to do a little more than that. So we've got a rod geometry, but we put different cross sections in. So we have a sort of square cross section, an octagon, diamond, a round, and then we've kind of put a paddle on the end of it. Brian's got a CAD file that he'll share here in just a second when the video's over to show you what we were trying to make. You'll see a picture of the final part here at the very end before we show the CAD file. So again, this whole thing takes sort of an hour to go completely run automatically. We're sort of only just sitting there with our hand on the e-stop in case it decides to try to hurt somebody. But otherwise, nothing really going on. I will draw attention to this kind of crazy looking space contraption that's on the end of the robot. This is a compliance device that Brian designed that allows us to have sort of compression and tension sort of compliance. It can also twist and rotate. So when we put these big forces on the part, it sort of protects the robot, and it works beautifully. And so it helps with set downs. And so this is really like the blacksmith's wrist, and the robot kind of becomes the elbow and the shoulder and the waist. So we gain some degrees of freedom there with this compliance device. So we're almost done here. I think there's about 15 more seconds, and then it's going to show the part at the end. You'll see me do a little cleanup on it. Yep, right here. So this is what we were trying to make. See, like any good video, we clean up after ourselves there. And then I'm gonna stop sharing, and Brian's gonna show you the CAD of the actual part we were trying to make. I don't know if we have a picture of them sitting side by side. I do in the presentation, but just for reference, that's what we were trying to make. You should see on your screen now. And we did some quick miking measurements, and we're within 2 to 4 millimeters in all sort of key dimensions on this part. So it would be pretty easy to throw this thing into a machining center and clean off basically the scale that's formed and get it to the geometry. And Brian's done some cool work on writing some code to sort of create templates for cast preforms. So if you know where you're trying to go, how do we cast something that's really close to where you want to go, and then just add a little bit more deformation. So that was part of the project as well. So we're really excited with the progress, and we're sort of ready to start smashing other things that have been made with other processes to really lean into the hybrid part of our hybrid autonomous manufacturing that is Hammer. I don't know if there are any questions if anybody wants to dig into any of that, but we had a good time.
Mm-hmm. And I was in the room for a bit of this, and it is great seeing big machines work, things going red hot and all of that. And again, this has value. The shapes like this you could make by additive manufacturing. It takes an awfully long time. And then it's a really efficient way of changing shapes for machining later. And I think we need to get into some cost modeling and so forth, but I'm sure there are significant savings that we can realize there. So thank you, Mike. And yeah, great job to the team over there. Really foundational stuff that, so far as I know, is nothing like this has ever really been done before, simple as it is.
Yeah, I think it opens the door at this point to at least like, so we haven't dug into the, let's call it the more science side of things. ARM is really focused on like making parts and transitioning technology now, but